Namaskar and hello. Welcome to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering education by clarity of concept and right understanding. Today in our playlist class 12th Physics and Physics Made Easy, we'll discuss few more multiple choice question on electrostatics. These all questions are very important and previously asked examination questions of various competitive exams. Let's start. 3-point charges plus 4q minus q and plus 4q are placed on x-axis at origin at a meter and 2a meter positions. We have to comment on equilibrium state of this charge configuration. On this smaller magnitude opposite polarity minus q charge at center, electrostatic attraction of plus 4q of position origin is shown by red arrow, and similarly attraction on minus q charge by this plus q charge at 2a position is shown by blue arrow, and these two forces are of equal magnitude and opposite direction, produce a equilibrium state of this minus q charge. Similarly, on this plus 4q charge, this 4q charge at 2a distance from it produce a electrostatic repulsion, and this minus q charge at a distance produce electrostatic attraction, and again two forces are of equal magnitude and opposite direction create equilibrium state for this plus 4q charge, and on same similar ground this plus 4q is also in equilibrium by two equal and opposite forces produced by respectively minus q and plus 4q on this 4q charge. So all three charges are in equilibrium, but if the charges are disturbed from their equilibrium position, say this minus q is displaced to any side on this x-axis towards either this origin charge or towards 2a meter position charge, it will get attracted towards that direction. So this equilibrium is not a stable equilibrium, it is a sort of unstable equilibrium. So all three charges are in unstable equilibrium. So this option 3, all charges are in unstable equilibrium, is a right choice for this question. A charged particle has mass m and charge q and it is at rest. If this particle is accelerated in an uniform electric field of strength capital E, determine its kinetic energy after y displacement in electric field. So in these questions, if we can find out potential difference in uniform electric field, we can find out work done on charge by electric field, as potential difference delta V is work done per unit charge. So if q charge accelerate by delta V potential difference, then work done by electric field is product of charge and potential difference, and this work get converted into gained kinetic energy, and potential difference in uniform electric field with y displacement is product of field strength and displacement. So work done become QEY, and this become gain in kinetic energy, and this option 3 become right choice here. We can also get answer of gained kinetic energy by work done in electric field. Q charge in uniform electric field of strength E have a force QE, and with force, if it makes y displacement along direction of force, then amount of work done would be QEY, and this work done become gain in kinetic energy. Again option 3 can be explained. At 4 vertices of a square, point charges minus capital Q minus small q plus 3 capital Q plus 2 small q are placed. Now it is found that resultant electric potential contribution by these 4 charges at the center of this square comes as 0. Then we have to find out a relation between magnitude of small q and magnitude of capital Q. So it's a very simple question based on trick of symmetry of source charges with respect to observation position, as here all these source charges got identical x distance from observation position, then their resultant electric potential as per superposition principle can be obtained by summation of all charges, and this summation charge at this x distance produce this potential, and if this resultant potential is 0, then summation of all 4 charges is 0, and this summation plus 2q and minus q become plus small q. Similarly, plus 3 capital Q and plus minus q become plus 2 capital Q. So plus small q plus 2 capital Q is 0 for resultant electric potential 0 here. So this first option become a right choice between magnitude of small q and capital Q. Strength of uniform electric field capital E is directed in plus x direction, and a positive plus 0.2 coulomb charge is displaced by 2 meter distance, making an angle 60 degree with electric field direction, and total amount of work done is 4 joule. Then we have to determine strength of this electric field. Now we know when force and displacement got certain angular deviation, then amount of work done is given as dot product of force and displacement. Now force on Q charge in electric field is QE, and when QE force and displacement got an angle theta, then dot product is force multiplied by displacement and cosine of angle between the two. So here with 60 degree angle cos 60 become 0.5, displacement is 2 meter and force is 0.2 E, and total amount work done is 4 joule. And when we simplify this expression, we will get that electric field intensity comes as 20 Newton per coulomb or 20 volt per meter. An electric dipole with dipole moment, product of charge and distance between charges, capital P, is placed in an uniform electric field with dipole moment making an angle theta with uniform electric field. We have to find out expression of torque on this electric dipole. Here positive Q charge will have a force in the direction of electric field QE, and this negative Q charge have equal and opposite QE force, and these two forces of equal magnitude opposite direction but not acting on the same line form a force couple, and that couple will try to rotate this dipole moment, and rotating torque exerted on dipole by uniform electric field force couple is given as product of force multiplied by normal perpendicular distance, and normal perpendicular distance between force lines is, if this is d and this angle is theta, then this is d cos theta and this normal distance become d sin theta. So torque is product of force QE and normal perpendicular distance d sin theta. Now the product of charge and distance become dipole moment capital P, so torque can be expressed as P sin theta, and in vector notation we can express torque vector as cross product or vector product of dipole moment vector and electric field intensity vector, and cross product of these two vector is magnitude of first vector, magnitude of second vector, and sine of the angle between dipole moment and electric field intensity, and which is theta in this diagram. Now this torque has a tendency to rotate dipole and to bring a position where theta become 0. Now theta 0 position will result in 0 torque or 0 rotating tendency, and that particular position is called as stable equilibrium. Similarly for theta 180, resultant torque on dipole in uniform electric field becomes 0, but in that condition if you disturb dipole, it will not attain previous position, will try to attain theta 0 position. So theta 0 is called stable equilibrium position, and theta 180 again of torque 0 position is called unstable equilibrium position. And for theta 90 degree, when dipole moment become perpendicular to electric field intensity, sin theta become maximum and rotating torque tendency become maximum, and maximum torque exert on dipole of moment P in uniform electric field is P times E. An electric dipole of dipole moment capital P is placed in an uniform electric field of strength capital E in stable equilibrium. That means dipole moment direction and electric field direction got an alignment, and angle between P and E vector is 0. What is the amount of work required to get rotation of that stable equilibrium condition dipole to maximum torque condition? That means we have to find out total amount of work done in rotating dipole in uniform electric field from stable equilibrium theta 0 condition to maximum torque theta 90 degree conditions. We know when a dipole moment makes an angle theta with uniform electric field intensity, the torque exerted on it to retain theta 0 position is P sin theta, and against this torque when we make small displacement we have to do small amount of work done, and total work can be obtained by integration. And if our displacement is from stable equilibrium theta 0 to maximum torque condition theta 90 degree, the work can be obtained by integration. P being constant can be brought out of integration. Integration of sin theta become minus cos theta. With these two limits, it become minus cos 90 plus cos 0, that is cos 90 is 0 and cos 0 is 1. So the amount of work done become P, and the second option become a right option. Now to find out amount of work done from stable equilibrium to any theta angle position, this limit becomes 0 to theta, and this become with cos 0 1 P 1 minus cos theta. So if a dipole moment from stable equilibrium position is rotated by an angle theta, amount of work done become P multiplied by 1 minus cos theta. And if our rotation is from stable equilibrium to unstable equilibrium, that means from 0 degree to 180 degree, cos 180 become minus 1. So our work become 2P for rotation of dipole moment from stable equilibrium condition theta 0 to unstable equilibrium condition theta 180. A thin charged ring of radius capital R has total positive plus Q charge. If its 1/4 part AKB produce an electric field E at center O position, then what is electric field contribution by remaining ACDB section? So we know a uniform charged ring at its center produce equal and opposite electric field contribution from diagonal opposite elemental charge section, and resultant electric field become 0 at this center position. So if electric field intensity contribution of AKB quarter section is capital E directed in this red arrow direction, then electric field contribution of remaining 3/4 section ACDB will be equal and opposite to this section to produce resultant electric field 0 here. So electric field contribution of ACDB is again capital E, and it is directed from O to K, and this second option, amount equal to electric field of AKB and direction opposite to it in OK direction, will become our right choice. ABC is a isosceles triangle with side AC and BC identical of 2A dimension, and if plus Q charge is placed at all three vertices, then what is amount of work done in moving a capital Q charge from D position to E position, where D and E are midpoint of side BC and side AC. So from each charge they got half of 2A distance. Now this calculation become quite simple when we study or analyze symmetry of this configuration. Let's first find out potential at position D by 3 charges. Now this Q charge of position B got A by 2 distance. Similarly, this Q charge of position C got A by 2 distance, and this third charge got a separation AD. Now in this triangle, separation AD and separation BE is identical. So at E position, if we see electric potential by this Q charge at A by 2 distance, this Q charge again A by 2 distance, and this Q charge of B distance identical to AD, we will found that potential of D point and potential of E point in this symmetrical configuration are identical. So potential difference between D point and E point is 0. So amount of work done in moving any amount of charge become 0. So this fourth option become right choice. A semicircle arc of radius A has a uniform line charge density lambda coulomb per meter, and we have to find out strength of electric field at its center. If it would be a complete circular ring, resultant electric field will become 0. But for this half circle or semicircle charge distribution, resultant electric field is non-zero, and that can be obtained by using Coulomb's law and integration techniques. We consider a small elemental length dl of line charge density lambda having lambda dl charge, and this lambda dl can be treated as point charge, and this point charge at a radial distance produce electric field k lambda dl over a square as shown by this vector direction. Now there is a symmetrical position at B that also produce identical amount of electric field in radial outward direction. If we resolve axial component of these two electric field, both will come in the same direction and will simply get added up, whereas normal to this axis component of B position charge and A position charge are equal and opposite and will cancel out. So resultant electric field is in this resultant direction, and it is summation of these axial component, and if this angle is theta, then this angle is 90 minus theta, and axial component is cos 90 minus theta or sin theta, and we have to make summation of all these axial component. Now here dl upon a arc by radius is elemental angle subtended here d theta. So when this integration is made, k lambda over a is a constant brought out of integration. Sin theta got integration minus cos theta, and these two limits are 0 to 180 degree, and with 0 and 180 limits this become minus cos pi plus cos 0, that is minus of minus 1 plus plus 1, that is 2. So this electric field is 2 k lambda over radius a, and this electric field magnitude 2 k lambda over a is the same as electric field produced by infinite long line charge at a normal distance a from it in the center position, and the same result can be obtained here. In place of k, when we put 1 upon 4 pi epsilon, our result will become this option 1 here. Now to find out electric potential at this position, we could have used summation q techniques, and total charge of semicircle ring is lambda pi a, and electric potential will become k lambda pi a divided by a, or k lambda pi, which doesn't depend upon radius of semicircle arc. So potential contribution doesn't depend on radius of arc if it got constant line charge density. If a point charge small q is placed at one corner of this cube, then what is net flux across this cube? Now we can't use Gauss law, as Gauss law need a closed surface with charge enclosed in that. Now this charge is neither inside this cube nor outside, so it would contribute some flux, and we have to explore symmetry with respect to this charge position and this cube dimension. If we assume 3 more cube adjacent to this cube, one on top and two on two other side, again this charge is not inside these cubes nor it is outside, it is on their surface. So to make this charge position enclosed, we can consider 4 more cube and place those 4 cubes in front of these 4 cubes as shown in this diagram. Now this cube will contribute q upon epsilon charge from all this closed surface having 8 cube here. So q upon epsilon is total amount of flux across 8 cube, and flux across 1 cube is 1/8 of this q upon 8 epsilon. Now here 3 shaded portion get coincide with this charge position, so these 3 surfaces have no flux crossing, as E vector here and area vector become perpendicular to each other, and the remaining 3 faces of q become symmetrical to this charge position. So this total q upon 8 epsilon charge will divide equally among remaining 3 faces, one of this base position, this side position, or this front position. So from any one face, net amount of flux become q upon 24 epsilon. So we can use such symmetry. If this charge was on center of this face, we could have assumed one more cube on top of it, and from 2 cube total flux is q upon epsilon. So from 1 cube it become q upon 2 epsilon, and if this charge is placed at center of one side, we would have assumed 4 cubes, and from 4 cube flux would become q upon epsilon, and from 1 cube it would become q upon 4 epsilon. We have explained 10 different question patterns on electrostatics frequently asked in various examinations. Probably similar type of question will be asked in your examination too, so practice of such questions will definitely help you to score high marks in competitive examinations. We end here only with a note of appreciation for your viewing and promotion of our learning videos. Thank you very much.